Sir, hello, sir.
Yeah.
Sir, in Mahindra, some camera is in fault. So we are sitting 9 people. It is not
Yeah.
shown in the
That's okay. No problem.
that conference room camera was fault right now.
Okay. No problem. So you're able to see the screen, right? All of you?
Yes, yes, yes.
Okay. Good. Let's get started. But you are able to see my screen, right? In Mahindra.
Yes, yes, yes. We are seeing.
Okay. All right. So we have so far looked at the structure of materials, imperfections, and the mechanical properties. And that brings us to the first and most important study on failure of materials. Okay. And here we will talk about primarily something called a static failure theory and why we need failure theory and so on. We will establish and then we will talk about it. Okay. So in this, we will discuss certain aspects of the concept of a stress tensor and its invariants, and how then we will define the failure theories, different types of failure theories for ductile materials, brittle materials, and then we will define the quantity called factor of safety. And then you apply these things to components that have stress concentrations or notches. And then we'll see some application of these failure theories for design problems. Okay, so what is failure? So when we say failure, what is the meaning of the failure? Does it really mean the complete failure or ultimate fracture of a component, or is it not? And the second thing is, how does one define failure when you are dealing with a ductile material and a brittle material? Is the definition of failure the same when you are dealing with a ductile material compared to dealing with a brittle material? And so if you are an engineer, for engineering applications, what do we consider as failure? Right? The definition of failure itself is important, because depending on the definition of failure, we will be able to characterize or we will be able to classify a particular component or a particular system is safe to use or is it not safe to use. And then, are material properties important? Are material properties that we have discussed in the previous classes, are they important in order to assess failure of a component? So these are the questions that one need to ask before we move on to understanding failure. First of all, we need to define what is failure. We should understand what is the meaning of failure. Okay. For example, if you look at this picture here on the left side figure, you have an oil tanker that has broken into two pieces. Yes, obviously it is a failure. And on the right side here, there is nothing that has broken. However, the columns and the beams here that you see, they have buckled. They have got some permanent deformation, and hence, again, this is also considered failure, although the material is still intact. There is no breakage like this. So you can have different types of failures in structures where there is a complete breakage, like here, and whereas you have some permanent deformation, although it is not broken, but still we will consider that as failure. So now the question is, why do parts fail like this? Why do structures fail like that? Why this guy has only buckled but did not fail? Whereas why this guy has actually completely broken instead of giving me a sign like the one that on the right hand side. So the question that we ask is, why do parts or why do components fail? I think this is the single most important question that contributes to a rich scientific understanding of failure of materials. If we don't ask this question, why do they fail, then we probably would not have understood a large deal about the failure of the components. So from the mechanical engineering point of view, or mechanical design point of view, whenever we are talking about failure, we try to understand the concept of Morse circle, and from there we will talk about failure in a little bit more detail. Okay. So how many of you are familiar with the concept of Morse circle? Just raise your hand. Two. I only see 3 people. Huh? 4.
I don't know how to raise a hand. Sorry.
Okay. So there are only 2 people. There are some people who have lowered their hands. 3 people. Okay. So that means we need to discuss what do you mean by Morse circle. So we will talk about the Morse circle, but here if you look at this particular figure, this particular, the left side Morse circle is the Morse circle for uniaxial tension, and the right side Morse circle is for pure torsion, okay, or pure shear. And if you look at this particular picture, you will see that the points on the periphery of the circle are the states of stress oriented at an angle from the axis at which you have applied the load. So all that becomes a little bit more complicated unless I actually define what Morse circle is. So the idea is that you have a Morse circle, and we will talk about it in a couple of minutes. Okay, so don't worry about that. So maybe I'll take this opportunity. Where is I'm sharing my screens in a moment. So you're able to see my screen, right?
Yes, sir.
Okay. So let us talk about the concept of Morse circle. So before we discuss the concept of Morse circle, I would like to talk about stress at a point. Okay. So when I'm talking about stress at a point, if you look at this bound, I moved back to my slides again, just to drive the idea of the concept of stress. So we are looking at a body, an arbitrary body, which is constrained at some point and which is subjected to some external force, right? And now if I look at an infinitesimal point in the body, and then this is what I am drawing it as an infinitesimal volume element. Is that clear? This is my infinitesimal volume element. And if I look at that infinitesimal volume element, I can show my stress state at that point as See, for example, this is your x-axis, y-axis, z-axis. To this plane, the normal to that plane is x-axis. Can you see that? Similarly, normal to this plane is y-axis. Normal to that the front plane is z-axis. Is that clear to all of you?
Yes, sir.
Yes, sir.
Yes,
Yeah.
sir.
So now, on this particular surface, you will have sigma xx. The first index is to represent the normal to that particular surface on which you are representing this. And the second index is in the direction in which it is being represented. So this is sigma xx. That is what we call normal stress because it is in the direction normal to the plane. Right? Sigma xx. And in this plane, the plane's index is x. And this is in the direction of y. This is what we call sigma xy. And this is sigma xz. These two components that are represented by white color are in the plane. That is why they are called shear stress components. Okay. So you have a normal stress component and two shear stress components. Similarly, in all the 6 phases, you can write them and then you will see that this is sigma yy, sigma yx, sigma yz, sigma zz, sigma zx, sigma zy. Is that clear now? Then the stress state at a point is represented by an infinitesimal element is given by this particular matrix called a stress tensor. It is not a matrix actually, it is a tensor. A tensor, strictly speaking, it is a second order tensor, which requires two indices to represent each and every element. Sigma xx, sigma yx, sigma zx, sigma xy, sigma yy, sigma zy, sigma xz, sigma yz, sigma zz. Okay, the first column represents this vector, second column represents this vector, third column represents that vector. Right? The entire thing together is what we call stress tensor. Okay. Now, so on any plane, you have one normal component and two shear components. That concept is clear to all of you?
Yes, sir.
Yeah. So now let me go back talking about our Morse circle. We need to introduce the concept of Morse circle. So if I take a two-dimensional state of stress, then instead of drawing a cube, I will draw a square. On that, I'll show that is my sigma xx. This will also be sigma xx. That is sigma yy. That is sigma yy. And that is sigma xy and sigma yx. This is also sigma xy and sigma yx. Right? So this is a two-dimensional state of stress, which is represented by a second order stress tensor, sigma xx, sigma yx, sigma xy, sigma yy. Right? Maybe these two quantities are coming here. These two quantities are coming. Okay. This is called a second order tensor. What do you mean by second order? Suppose if you take a vector, how do you represent a vector?
Magnitude and direction.
By direction and magnitude.
So let us look at this fellow. let us say you have x-axis and y-axis. I am drawing a vector v. So how do I represent this vector v? So let us say this is how many units? Oops. And this is 1.5 units, correct? So v can be written as 3 1.5. Can I do that? Can I do that or not? Do you agree? So here Vx is equal to 3, Vy is equal to 1.5. That means Vx is the projection of the vector v on x-axis. Vy is projection of v on y-axis. So whenever you are writing a vector, the components of the vector represents the projections of that vector onto the respective coordinate axis. Okay. So now if you look at this fellow, v 3 1.5, the magnitude is what? Square root of
3 square plus 1.5 square.
5 square. And the direction? Direction, typically, you just represent what is this angle. So, theta is equal to tan inverse Vy by Vx. That is equal to tan inverse 1.5 by 3. That is equal to tan inverse 1 by 2. Right? So that is how you represent the vector. So if you write this vector, there is another way to represent this vector, right? This vector will have how many components? 2 components here because it's a 2D system. So you say that V1 and V2. V1 is your 3, V2 is your this thing. So whenever you are representing this vector, I could represent vector as V, or I could also write as Vi, where I goes from 1 to 2. Can I say that?
Yes, sir.
So in order to represent the vector, how many indices am I requiring here? There is only need for only one index. That is why it is called a first order tensor. Because I need only one index. Whereas coming to a stress tensor, if I have to represent this guy, I have to say sigma 1 is sigma xx, sigma 1 is sigma yx, sigma 2 is sigma yy. Correct? Meaning the particular index value, first row, first column, first row, second column, second row, second column, and so on. So in order to represent sigma, I could write sigma, or I could write sigma ij. Since I need 2 indices to access any element, then that is called a second order tensor. Okay. Fine. So now you have sigma, which is given by sigma xx, sigma xy, sigma xy, sigma yy. Here xy have written because it is symmetric. Although we have not used that thing anywhere, but this is a symmetric tensor. That is why sigma xy can be written as sigma yx. Okay. Now, Carefully observe. For this below, whatever we have written here, that is our x-axis and that is our y-axis, isn't it? So, what is the, suppose if you look at this particular surface, what is the normal to that surface or normal to that edge?
Sigma x6.
Sorry?
Sigma x6.
No, what is the normal vector? How do you represent the normal vector? What is the normal vector to that?
X.
X-axis, isn't it?
Yes, sir.
Is the normal in the direction of x-axis or not?
Yes, sir.
Yes,
X1.
sir.
Yeah. So what is the unit vector along x-axis?
I.
Whenever I say vector, it will have how many indices? How many components? It should have, it's a two-dimensional space, so we have to have two components. So let us say that unit vector along x direction is E1, E1 hat. That will be 1, 0. And unit vector along y direction is E2 hat, that is 0, 1. Do you agree or not? Is there any question here?
No, sir.
Okay. Now, the stress state at this point. Okay, let me. The stress state that is shown on this infinitesimal element can be represented by sigma is equal to sigma xx, sigma yx, sigma xy, sigma yy. And if that is dotted, this is the dot product of that with E1 hat. E1 hat is 1, 0. What will I get?
Sigma XX. Sigma XX.
Is it?
Sorry, plus
Plus
sigma y
XY.
xy.
Plus sigma xy or is a 2 by 2 matrix? It is a 2 by 1 matrix. What should you get?
Sorry,
2 by 1. Sigma
2 by
XX
1.
and sigma
Sigma x and
xy.
sigma xy.
Sigma xy. What did we get? When I have taken this matrix, second order tensor, and if I find projection of this vector onto a plane whose normal is this. What is that plane? That is this plane, isn't it? Because the plane's normal is 1, 0. Then I am getting this. That is basically these two components, isn't it? So
Yes, sir.
this is what we call, this is also a vector, isn't it? This we call a traction vector. So the traction vector on any plane n is given by stress tensor dotted with normal to that vector, normal to that plane. That gives the traction vector on that plane. Okay, T is equal to sigma dot n will give you traction vector on that plane. Meaning, if you look at this fellow, on this plane, I am plotting again that particular, I am only drawing that particular plane. Okay. On that plane, I have two components. One component is sigma xx. Another component is within the plane, that is sigma xy. If you have two components, the net will be some vector that I call t. And what is the normal to this particular one? The normal is E1 hat, so I call t E1 hat. That means the traction vector on a plane whose normal is E1 hat is given by these two guys, sigma xx and sigma y. So t E1 hat is equal to sigma xx, sigma xy. E1 hat is the normal to the plane. So when you take full stress tensor, multiply that with the, find the dot product of that with the normal to any particular plane, then that gives you traction vector acting on that particular plane. Is that clear?
Yes, sir.
Yeah. Now, so on any plane you have a state of stress which is a normal stress and normal component and shear component. If it is 2D, you will have one normal component and one shear component. Is that clear? In general.
Yes, sir.
Yeah. So what your Mohr circle says is that the following. You take your x-axis as normal component of the stress, y-axis as the shear component of the stress. Okay. Now, on any particular plane, you have sigma xx comma sigma xy. Agreed? So identify that particular point. Let us say that is your sigma xx comma sigma xy. Okay. Now look at the other plane here. That is highlighted by the pink one right now, which is at an angle 90 degrees to the original plane. So let us say this is a state of stress at a particular plane. Now we are looking at the state of stress at another plane, which is at 90 degrees. The state of stress is what? Sigma yy and again sigma xy. Both of them are same. So if it is 90 degrees in the physical plane, in the Mohr circle, it will be 2 times theta. That means 2 into 90 is 180 degrees. So all that I need to do is, let us say this is my sigma xx. Then all that I need to do is I need to draw a line. This is sigma xy, right? And sigma yy will be somewhere, right? That is a normal quantity. So this is sigma xx, and this is sigma xy. And this is the sigma xx value. That is why you got this point. And your sigma yy could be positive or negative. Let us say sigma yy is this for some reason. Okay. Value of sigma yy is this. Then sigma xy should be in the negative direction. Then you join a line. Then this is your sigma yy comma sigma yx. Okay. You do that, then you got stress state at on one plane and stress state on a plane which is at 90 degrees to that particular plane. You got that. Then you draw a circle connecting these 2 points. Okay. And that is your Morse circle. And that Morse circle will intersect x-axis or your sigma y. Intersect your x-axis at these 2 points. This is what we call sigma 1 and this is what we call sigma 2. The sigma 1 is maximum principal stress. This is called minimum principal stress. And this is where you will have maximum shear, tau max. Okay. Now, if you know the state of stress here, then there is an angle. This angle, let us represent as 2 theta. On this plane is at an angle 2 theta from the original, this particular plane. From this plane, I am looking at an angle 2 theta. Meaning, at an angle 2 theta, whatever may be that angle, you have this angle we can find out by what is the angle? How do you find out this angle? Because this is sigma xy by you know how to find out that angle using tan theta. This is what we call a principal plane. And that principal plane basically is telling you that on that particular plane there are no shear components, everything will be a normal component. Okay. Is this clear how we have drawn the Morse circle?
Yes, sir.
Yeah. And now any point on this Morse circle will represent the state of stress when this. So you have looked at a particular point. At that point, if the element is like that, then you have calculated your stress state like this. But instead of doing that, if you change your orientation, so instead of your orientation being like this, if you say that my element is oriented like that, that means your coordinate axis is like that. Then in that plane, what is the state of stress can be obtained from this Morse circle by just knowing the angle between these two fellows. If the angle between these two fellows is theta, then from here you choose another one which is at an angle 2 theta, and that will represent the state of stress at that point. Okay, like that, by drawing the Morse circle, you can find the state of stress at any point without worrying about calculations. Okay. So by Morse circle, you can see what is my principal plane and what is the maximum shear plane and so on. So that means always your plane at which shear stress is maximum will be at an angle of 45 degrees from the plane on which you have principal stresses. Is that point clear?
Yes.
Can you repeat the last statement?
So you look at this plane. What is this plane? That is what we call principal plane.
Principal plane.
That means on that shear stress is 0. What is this plane?
Max shear plane.
It's normal to the principal.
Normal.
No, this plane represents the shear stress
Shear.
in this plane. The shear stress is maximum compared to any other plane. This is the maximum shear stress plane. Okay. Now, in the Morse circle, the principal stress plane and maximum shear stress plane are at an angle of 90 degrees. Correct?
90 degrees.
Which means physically, in actual material, the angle between principal stress plane and the maximum shear plane will be 90 by 2. That is 45 degrees. Did you understand that?
2 theta equal to 90, right? So
Yes.
theta you're saying as 45.
Yes. Is that is convincing or not? Okay. Now, if that is the case, let us try to carefully understand this. Let us say your uniaxial tension test. Okay. How do I do a uniaxial tension test? I have a specimen. I apply sigma. That's all, right? So for this, if I have to write the stress tensor in that particular orientation, what will it look like? Let us say that is my x-axis, that is my y-axis.
Sigma.
0, 0, 0, sigma. That is the stress tensor, isn't it? Because there is no shear stress. Agreed?
Yes, sir.
Yeah. Now, if you carefully observe in this particular plane, the shear stress is 0. Can you see that? Therefore, this is the principal plane. Do you agree? Then this plane is principal plane in the paper. So that means sigma 1 is equal to sigma, and sigma 2, the minimum principal stress is 0. Maximum principal stress is sigma, minimum principal stress is 0. All of you, do you agree with that?
Yes, sir.
Yeah. Now let us draw the Morse circle. In Morse circle can also be drawn if we know the principal stresses directly. You identify the principal stresses and connect a circle between the principal stresses. That is how you draw the Morse circle. So let me draw first. Okay. So what is sigma 1? Sigma 1 is some value sigma. Sigma 2 is 0. 0 is this, right? This is sigma and that is tau. So this is my sigma 1. This is my sigma 1. That is my sigma 2. Correct? So how do I draw Morse circle? I just have to draw a circle connecting these two fellows on the periphery. That's my Morse circle, isn't it? So, if that is the case, this is my tau max, isn't it? and which is at an angle 2 theta. That means the plane on which shear stress is maximum is at 45 degrees to the principal plane. So this is the plane. So my x and y axis I am drawing again. That means my principal stress is in along the y direction. So the shear stress will be maximum along a 45-degree plane. Along that plane, you will have maximum shear stress. That's what it means, isn't it? Yeah.
Yes, sir.
And that is the reason why whenever you take a ductile material and apply a tension load, there will be failure happening at an angle 45 degree. The failure will not happen like that. Failure happens at an angle 45 degree because the shear stress is maximum there. We will see why shear stress plays a role there. Why shear stress important for a ductile material, we will see later. But the 45-degree serrations that you will see on the plane is because of that. Okay. All right. So this is the Mohr circle for uniaxial tension. What this basically is telling us is that although in the material I am applying pure uniaxial tension, there are planes oriented at an angle to the principal stress plane, which will have some shear developed on them. Although the microscopically I am only applying tension, but in that plane only you are applying tension. There are other planes which are experiencing shear. That is what this is telling us. The Mohr circle is explaining us that very neatly. Similarly, if you are doing only pure shear like torsion, so the pure shear implies the principal stresses are opposite signs. Sigma 1 is equal to minus sigma 3. And minimum principal stress is 0. So let us say the first, they are opposite sign or minus sigma 2. That means if this is your sigma 1, that will be your sigma 2. Then if you draw a circle, and then you will have, this is your sigma max, tau max, shear stress, maximum shear stress. Right? So this is what we call Mohr circle for pure shear. That means you have a situation where there is only shear stress, there is no normal stress at all. That is why it is called pure shear. Although there is a point at which you only have pure shear, there is no normal stress at all. There are planes at which you will have a combination of normal and shear stress or only normal stress. Suppose if you look at this fellow, is there any point in this fellow where you have pure shears, scenario of pure shear? What do you mean by pure shear? At that particular point, your normal stress has to be 0 and only shear stress should exist. There is no such point. So that means when you are applying uniaxial tension, you will have simple shear, but you will never have pure shear. Okay? By looking at Mohr circle, you can answer all, you can sort of make certain observations about your behavior of the stress state. Any questions?
Sir, if we take into account Poisson's ratio actually, and then you will also have a component that is like in the other direction also, right? So
No, we are only talking about the two-dimensional state of stress. Whenever you have a 3D state of stress, then that comes into picture. That we are not looking at. Okay?
Okay.
Yeah. That we will talk about. Hello?
you're audible.
Can you see the screen, right? Yeah.
Yes, sir.
Okay. So now, if you look at this Mohr circle, you can, if you know sigma x, sigma y, sigma xy or tau xy, then you can calculate the normal and shear components like this, where you need to plug that value, and then you'll be able to identify the stress state at various locations. That's this formula. You can go through it. It is you would have learned it in your BTECs. Okay. Now, how do you draw Mohr circle for 3D? So whenever you are dealing with a three-dimensional state of stress, you will have three principal stresses. Instead of two principal stresses, you will have three principal stresses. That is sigma 1, sigma 2, and sigma 3. When you had only two principal stresses, what did you do? This is sigma 1 and that is sigma 2, and then you just drew a circle between sigma 1 and sigma 2. That is one Mohr circle. But if you have three principal stresses, what you can do is you can identify sigma 1, sigma 2, and sigma 3. Then draw a Mohr circle between sigma 1 and sigma 2. Another one between sigma 1 and sigma 3. Another one between sigma 2 and sigma 3. And the area represented in the green color is what we represent as the valid area for the stress state. So this is how we identify the Mohr circle for 3D. Then you know, depending upon the state of stress, then we will be able to figure out what kind of stress state you are going to have at various orientations. And here you can see the maximum shear stress will be sigma 1 minus sigma 3 by 2. Where sigma 1 is the maximum principal stress, sigma 3 is the minimum principal stress. Okay. Now, if you are doing a static tensile test, in general, the ductile materials are limited by their shear strength. Why? Whenever we are talking about failure, for a ductile material, the failure is defined or defined by onset of plastic deformation, because once the plastic deformation begins, then your component is considered to be not delivering what functionally it is to be delivered, because there should not be any plastic deformation in the material. So when the plastic deformation onsets, that is when you consider a ductile material has failed. How does plastic deformation begin? What is the mechanism for plastic deformation in a ductile material?
Shear.
Dislocation motion. Right? Dislocation motion is that for a crystalline material, it is represented as plastic deformation. How does dislocation motion take place? Dislocations move under shear, right? So that is why they are limited by their shear strength. Whereas in brittle materials, there is no dislocation motion, and hence the failure is represented by complete fracture. The fracture means normal strength. That should be the atoms should be separated from one another. That is why brittle materials are limited by their normal strength. Since ductile materials are limited by their shear strength and brittle materials are limited by their normal strength, the same kind of condition which governs the failure of ductile materials cannot be used for brittle materials. That means the same kind of failure theory does not explain the failure in all the materials. So, depending on the type of material, a class of materials, you have to develop different failure theories. So, okay, we know that there are mechanisms are different and hence you have to develop different failure theories. That is fine. But before we actually talk about a specific failure theory, we need to develop a proper definition of failure, as we were discussing. A ductile material is something that is, it is defined, a material is considered a ductile material if the percentage elongation up to fracture is greater than 5%, and some materials it is up to 10%. That is how you define a ductile material. So, if you are talking about a component, it can be considered to be failed if it yields or plastically deforms, leading to improper functioning. In some cases, the component may fail by fracture. As we discussed, both are failures, but the mechanisms are different. And in addition to this, whether this failure, whether by yielding or by fracture, is it happening because of the static load or a varying load? All these things will determine how we are going to talk about failure in a material. As we have discussed, we will first focus on ductile materials and we will only focus on static failure in this module. So the ductile materials fail by fracture if loaded beyond the ultimate tensile strength. But most of the machine components which are made of ductile materials, they are considered to be failed if they cross the yielding or plastic deformation. Or so the yield strength of a ductile material, you know, is much less than the ultimate tensile strength of the material. So now let us look at this scenario. You take, this is pure uniaxial tension. Here you have a uniaxial, it's a biaxial loading, but in one direction it is tension, in the other direction it is compression. This is equibiaxial loading and this is equitriaxial loading. And if you look at the stress strain curve in these systems, what you would observe is when the yielding, the plastic deformation begins when applied value of sigma is equal to yield strength of the material in this particular case. Whereas in this particular loading scenario, the yielding begins, that means the plastic deformation begins when this value is 1/2 of the yield strength of the material. In this case, again, when the load is equibiaxial, again the yielding happens when the value of sigma is equal to yield strength of the material. And in this scenario where you are applying equitriaxial compression, in all the three directions you have equal value, then the material is not yielding at all. You see here, depending upon the type of loading, you are required to apply certain load in order for it to cause yielding, and the applied load, the load to be applied is not the same. In some cases, you have to apply larger load to cause yielding. In some cases, you have to apply much smaller load to cause yielding. Now the question is, how do I decide? I know only for a material, yield strength is only one uniaxial quantity, one scalar value. But in reality, a material is subjected to a complex 3D state of loading. If it is subjected to a complex 3D state of loading and the stress value at which it is yielding is different from what it is doing in a uniaxial case, then how do I now characterize failure? Do I develop theory for different types of loadings? Or should I have a theory which should work irrespective of the type of loading. Ideally, it should work without worrying about the type of loading, whether it is uniaxial loading or biaxial loading or a triaxial loading. Your theory should be able to predict failure in the same way. That means the formulation should not change. Then only the theory is robust theory. Right? So the idea is now we see that now you cannot simply use yield strength. You cannot say that when the applied yield strength is greater than, so when the applied load is equal to yield strength, that is when failure happens. I cannot say that, because in this case, when the applied load is 1/2 of the yield strength, that is when failure is happening. I cannot make such a statement. So I have to make much more complicated or much more sophisticated statement. Let us see what sophisticated statement that we can do. But in order to develop such a theory, we have certain assumptions. The assumptions that we are having in this work are, there are no cracks in the material. That is the first assumption. And the second one is the material is isotropic and homogeneous. These are the two fundamental assumptions. With these assumptions, we are going to develop a failure theory. All right. So what is the general form? How does this failure theory look like? So we know the resistance of a material to yielding is given by something called a yield strength of the material. And if the failure is to be represented by the ultimate strength, that is when the fracture is happening. Your failure criterion for an isotropic material can be expressed as some function. That function depends on sigma 1, sigma 2, sigma 3. These are three principal stresses. These three principal stresses are unique for a given state of stress. So if you develop a functional form which depends on sigma 1, sigma 2, sigma 3, and when that functional form becomes equal to the failure strength, if it is ductile material, the sigma c will be yield strength. If it is brittle material, that sigma c will be ultimate tensile strength. So if we can develop a functional form like that, that will be really useful, without actually worrying about whether you have applied uniaxial state of loading, biaxial state of loading, or triaxial state of loading. This functional form should be able to capture that. And sigma c will be chosen whether it is a ductile material or a brittle material. So that is the kind of a failure criterion or the theory that we are looking for to develop. Now the question is, why should I write this functional form as a function of sigma 1, sigma 2, sigma 3? Why should I write it as a function of principal stresses, sigma 1, sigma 2, sigma 3? Why not as something else? So the question is that you could write it in something else, but the idea is a valid failure criterion should result in the same outcome independent of the choice of the coordinate system. All right. So this, I think I will stop here today, because okay, well, let me spend 10 more minutes on driving this point. So why is the failure criterion written in stress space, principal stress space? I will talk about what do we mean by writing in principal stress space in a couple of in tomorrow's class, in next week's class. But a valid failure criterion, why we are doing that, should be independent of the coordinate system that you are choosing. What do I mean by that? That becomes clear in the next class. So in order to ensure that it is independent of the coordinate system, we are writing F in principal stress space, because that's an invariant quantity. What is an invariant quantity? I will talk about it in the next class. When you plot this function in the principal stress space, this will be looking like a surface in the principal surface, and that surface is called the failure surface. And depending upon the failure theories, each failure theory that we are going to talk about is only differing from each other by this functional form that you are using. What is the way that you are writing a function will decide what the failure theory is. So different failure theories are basically different choices for the mathematical form of the function f. So we trying to choose a mathematical form that matches closely with the experiments. Okay. So these are the various failure theories that we are going to discuss in this class. And each one of them will have different functional form for this particular equation. That's all. Okay. Maximum normal stress theory, normal strain theory, total strain energy theory, distortion energy theory, maximum shear stress. These are the failure theories that we are going to talk about in this course. I think I'll stop here and we will meet in the next week where we will talk about the invariants of the stress tensor, which is important to drive the point why we are writing the failure theories in the principal stress space. Okay. Any questions here? Okay, if there are no further questions, I know we are stopping early today, but we will leave it here because the next thing requires some continuous effort, so that we will do it in the next class. Okay.
Professor,
Read
one,
once.
Yeah.
in I think couple of slides back, you have shown the picture, right?
Yeah.
So there, the last one with all three compression loads. So why is that stress and strain in the negative direction? Yeah, in this one.
Yeah, because there is compression. I have shown compression instead of showing
Yeah.
tension. That's all.
Okay, all compression. So strain
Yeah.
and stress both are in negative.
Yeah.
Okay, Professor. Yeah, thank you.
Yeah. Okay. Bye.
Thank you.
Okay. Bye.
Thank you.
Sir, you will share the presentation, right?
Presentation is already shared in the
Okay.
folder. It is there.
Okay. Thank you, sir.
Thank you, Mr.
Thank you,
Thank you.
Thank you,
Thank
sir.
you, sir.